Okay, so it looks like we're recording. So here's where we were last time. We were looking at this non-homogeneous system of equations. Of course, we've got the system in matrix form because this is very convenient, right? Okay, and we've already talked about how to approach this. I mean, sort of, our, if you will, naive guess would have been, just looking at here I have an exponential times a constant vector. Naive guess would have been exponential times a constant vector. And we've already gone through a previous example where we see that it doesn't work in a certain sort of unfortunate circumstance where this number is an eigenvalue, the matrix is singular, and you can't expect to have solutions, right? And of course, that's the circumstance we have here. This is an eigenvalue for that matrix. Okay, so we decided to modify our guess by adding an extra term. Here, let me circle this better. There's my extra term. And why would I add that extra term in there? Well, because when I take a derivative of that extra term, one of the two terms that's created is of the same form that we ran into a dead end with previously, right? So this has the possibility to tinker with with our existing sort of stalemate that we were in before we added this term. So this gives us hope, at least. Okay, so we talked about all this last time. We then took our new revised guess, plug it in, see what happens to the equation. The equation becomes this. As usual, notice that the common factor of the exponential cancels. You can shuffle terms around, group like powers of x, and here's where we ended. We had these two equations. Okay, so I hope everybody remembers this where we were. This equation here is an easy one to solve. B is just any multiple of that eigenvector, right? We're looking at an eigenspace. I mean, A minus 4i right there. Okay. Again, now what I warned y'all against, last thing that I commented on last Friday, I guess it was don't pick this vector too quickly, right? It's tempting to say, oh, I get to pick any value of k I want. I'm going to choose k equals 1 because I like integers, right? Seems tempting. The problem is, whatever you pick for this b, that's going to go into here. That's going to affect what is your right-hand side in this equation. And we have a problem with this equation. In this equation, the singularity of this matrix is not our friend, it's our enemy. This is a problem, right? We have a singular matrix. It's a non-homogeneous system. We do not have a guarantee that solutions will even exist here, right? So what we're going to try to do is figure out how can we cleverly choose just the right value of this k, pick just the right b vector, that is, that'll allow this right-hand side to definitely have solutions. That's our hope. Okay. All right, and it's ultimately no big deal to do this. This equation, just recopy it like that. Notice I'm plugging in, b is that. Otherwise, it's the exact same equation. Let's write it out in detail. When we know what a is, we know what a minus 4i is, and this is what our equation becomes. We want to try to figure out under what circumstances, for what value of k, does this have solutions. And there's a couple different ways that you can proceed at this point. You may remember, long time ago, way back when we were talking about Chapter 1, and there were actually some questions that were of the form, hey, here's a matrix. The right-hand side has some variables in it. Figure out what are the appropriate values of those variables that under which solutions will exist. And the idea was you just row reduce. Identify your possible contradictions and choose whatever the variables are. Choose them such that any possible contradictions won't be contradictions. In other words, anything that it better be 0, just choose it to be 0, right? And then give you conditions on k. So you can totally take that approach. Works just fine. I'm going to show you a different way to do this that I think is nice. And that is, to look at the left side and notice that when you multiply this out, notice that the first component of the right-hand side and the second component of the left-hand side, first and second components of the left-hand side are in a 3-to-2 proportion. And that means that the right-hand side, the first and second components of the right-hand side also have to be in a 3-to-2 proportion. So it's kind of it's a way to cleverly bypass the row reduction. Row reductions are nice. They always tell you all the solutions and everything, but cleverness can sometimes bypass some of that effort. So, in the past we've made rank arguments to bypass row reductions. Here we're ultimately making some observation about the column space of this matrix. The column space is in the direction of the vector 3, 2. Right? Capitalizing on that tells us, what has to be the case for our right-hand side. Okay, let me take a pause here before I go on. Is everybody okay with my assertion that this must be true if there's going to be a solution? Okay. All right. And now it's easy algebra, right? You cross multiply and solve for k, and there you go. K is 4/5. Once you know k is 4/5, that tells you what b is. Right? Once you know what b is, now you know what your system is that's going to allow you to solve for a. It ends up becoming this, and so now you solve this system, and it's an easy system to solve. Again, we already knew this was a singular system. We already knew that there was really ultimately only one equation here. In other words, when you row reduce this, there's a single equation, and then there's a 0 equals 0. So that single equation, if you multiply this out, is equivalent to that. And so here you really can just kind of pick whatever value of A1 and A2 you want. It doesn't matter. We've already got our B worked out. And there you go. A and B are picked, and therefore our solution is that. Okay. How are we doing? Questions? All right. Okay, so reminder, the way to solve these kinds of equations, very often, here's a homogeneous, but if you have a non-homogeneous term, make a reasonable speculation on the form that the solution ought to take, plug it in, and then solve for your undetermined coefficients. It's really very much like section 4.3. The big difference, of course, being that we don't have our big theorem telling us exactly what to guess that definitely will work. No questions asked. We don't have that big theorem, but the guess and check sort of strategy still works just fine. And then be prepared for unfortunate coincidences and the possibility that you might have to add in an extra term to give yourself the flexibility. Okay, moving along. So this is our, I guess I better zoom in one more. This is our last section. There's really there's a few ideas in this last section. There's sort of one computational tool and then some neat observations to make about it. It starts off with a flashback to chapter 4, and y'all remember these equations. And we know how to solve these equations. We don't need more help solving these equations. We've got a technique, right? Characteristic polynomial, roots, multiplicities, non-homogeneous, particular solutions. We're all good in some sense. Nevertheless, I'd like to show you a different way that you could solve these equations. It's kind of clever. Not clear how useful it is, but it's clever. And that is, I'm going to start with this observation that I've got written here. Everything in this equation is at most a first derivative. And that seems patently wrong. Right? Look at this. There's a third derivative right here. Don't tell me that that's just a first derivative. This isn't just a first derivative. And then my smart alecky response is, well, it is a first derivative. It's a first derivative of y double prime. And, right, I mean, it's just very smart alecky, very seemingly pointless, but you gotta give it to me. That's technically true, right? This y triple prime is a first derivative of y double prime. Now, how do you make that useful, we ask? So, I'm going to make up three new variables. These are the things whose values and first derivatives only contribute to the original equation. I'm going to take these three things. I'm going to give them names. I'm going to give them names. I'm going to call these U0, U1, and U2. And having done so, noticing that U0 prime is U1, U1 prime is U2, and noticing that U2 prime, U2 prime would be Y triple prime, which is that which I can solve for in the original equation. And all together, throw it all together, and what you have is formulas for the first derivatives, specifically the first derivatives of U0, U1, and U2, all in terms of U0, U1, and U2. So, in fact, what we have here is a first order system. Technically, I mean, this is true, right? I mean, this works. What we have then is sort of a computational alternative if you don't want to solve a third order equation. Play this little smart alecky trick, and an alternative is to solve a first order. Okay, it's a system, right? So there's a trade-off. Yes, we reduce the degree, third order turned into first order. That's the good news. The bad news is one equation turned into three equations. Nevertheless, it's an option. Okay, so who would do this? Right. So let's think about our options. Here, if I wanted to write down the characteristic polynomial, how do I proceed? Well, I read the coefficients of the characteristic polynomial straight off of what's written down. It's a freebie, finding that characteristic polynomial. How do I compute this characteristic polynomial? Well, I've got to take the coefficient matrix and I've got to say minus lambda on the diagonal entries, and then I've got to compute a determinant. And so there's quite a bit more work that goes into it, right? What do I do if the roots have multiplicities here? Oh, I have an explicit theorem that says, boom, boom, here's exactly what to write down. What do I do if one of these roots of the characteristic polynomial, namely eigenvalues? What do I do if one of the eigenvalues that I end up with here has a multiplicity? Well, I've got to worry about it. All right, I better hope that the matrix is still diagonalizable. It might not be. It might be a Jordan situation, in which case I've got to figure out how do I find a Jordan basis, if I even can. Right? So all else being equal, but given the choice between these two, which one do you pick? You got to go with this one, probably. Right? Okay, so I want to emphasize here this connection between these two separate equations. I'm not saying that, here, write it like this because this is the better way to solve. No, certainly not. Right? I'm just making the observation that these two questions have equivalent answers. Okay. So, specifically then, if you find a solution to that system, right, then y, namely the first component of that solution vector, that's a solution to this equation. That's all I'm saying. Okay, everybody good so far? All right. Now, next observation I want to make, this is a really surprising fact. This almost seems implausible. So, suppose you take a Chapter 4 style equation, homogeneous, and suppose you convert it into a chapter 6 style system, also homogeneous, of course, as described on the previous page. Suppose you do this. Suppose you then subsequently write down the characteristic polynomials. Of course, for this, the characteristic polynomial is just a matter of recopying. That characteristic polynomial is easy, right? On the other hand, if you were to take the other system, look at the matrix, subtract lambda I, take the determinant, right? Go through the whole process, ... You get this other characteristic polynomial. And here's a remarkable theorem. Really weird theorem. These two polynomials are always equal. And that is, I think, at a glance, I think that's quite stunning. Right? This should be a big eyebrow raiser, like, whoa, hey, whoa, how could, this is highly unexpected. We had no suggestion at a glance that this should happen. What's going on here? Right? Here's why it's unexpected, by the way, just to emphasize, what we're saying is if you take these coefficients here, if you go through a weird process to write a matrix out of them, in a weird way, described on the previous page. Then if you take that matrix and go through this further weird process of making a characteristic polynomial, the fact that you get the same thing back that you started with is really very unexpected. Okay. All right. Perhaps you don't believe me. Let me just show you a quick example. So, differential equation, characteristic polynomial. Super easy to write down. But now let's go through and play that game. If you were to turn that differential equation into a chapter 6 style system, this is what you get. Now, that's a nice exercise that y'all can do. You know, take the method on the previous page, interpret everything in this question, everything in this equation here as being at most a first derivative. Right? That tells you what your new variables u0 and u1 are, and put them together and make a system, and here you go. So make sure you can do that. And then further from there, take that matrix, right? Subtract lambda on the diagonals. Take the determinant, right? This whole game, and look what comes out. Lo and behold, same characteristic polynomial. All right, I think this is super weird. It's a real eyebrow raiser. Now that I've hopefully persuaded you, at least in some sense, that this is unexpected, let me show you why, in fact, this is not that unexpected, and this is actually entirely plausible, and in fact, something that really should be true. And this is an easy sell, as it turns out. You just got to look at it the right way. Keep in mind that when you convert, right, the whole point of converting a chapter 4 style equation into a chapter 6 style system was that when you solve them, you get the same answers. I mean, in a sense, right? I mean, obviously, the solutions to the system are vectors, but if you look at that vector and look at the first coordinate, u0, that u0 is the y. That was the solution here, right? So in this sense of the word, you get the same solutions. And then we'll just think about, wait a second, in each of these cases, where do solutions come from? Ultimately, in both cases, these solutions come from that characteristic polynomial, and these solutions come from this characteristic polynomial. Right? I mean, there's different details, but back in chapter 4, you write down the characteristic polynomial, you factor it, you infer from the factors, you infer the roots tell you the solutions in a certain formula. In chapter 6, you write down the characteristic polynomial. It's a different characteristic polynomial. It's a different game, right? It's that whole determinant of a minus lambda I, that whole eigenvalue thing. Nevertheless, you write down this polynomial, which you then factor to find the roots. Those roots are the eigenvalues. The eigenvalues, many details, of course, follow, but ultimately the eigenvalues are going to tell you the solutions. Right? In fact, if if both of these polynomials have no repeated roots, it is quite simple to write down exactly what the solutions are that this characteristic polynomial gives, exactly what the solutions are that this characteristic polynomial gives. The only way they could give you the same solutions is that they were the same roots, therefore the same factors, therefore the same polynomials. It's extremely plausible if you think about it this way. It's a little harder to deal with if there's multiplicity. So I don't want to get off into the weeds of how do you prove this theorem in the case of roots having multiplicities. Things get a little bit more complicated, but it's just details. The intuition is what I've got here. Okay. Okay. So back to where we were before. Instead of solving a chapter 4 equation, you have as an alternative to solve a chapter 6 system. This is still the easier way to do it, right? Hopefully I've at least raised an eyebrow a little bit for you as to, well, even though this doesn't make it easier, there is something very natural about this because, again, the characteristic polynomials, they're all the same. Wow. But the question remains, if this is still harder, then why do we care? Right? So the answer to that question is a common story in math. And this is something that I want to encourage you all to always be on the lookout for in other contexts in the future. Sometimes when you see a connection between two different kinds of math ideas, the immediate application is not the point. The point is that this is a suggestion, this is a first step in a direction that even if that wasn't useful, but keep going in that direction. That same idea applied in other contexts could be crazy useful. And that's what we're about to see here. So let's look at this question here. Let's look at this system of equations. And we have to admit, at this point, up to now, we have no idea how to solve this system of equations. Right? I mean, this is a system that's not first order. The only systems that we've ever talked about how to solve are first order systems. This is second order. Right? So we don't have any techniques. We don't know what to do here. We're out of luck. And then you say, oh, yeah, but look, back in chapter 4, we did all sorts of second order, third order, nth order back in chapter 4. Yeah, that's true. But that was one equation. This is two equations. This is a system. Nowhere in chapter 4 did we talk about systems. So this is kind of a, if you will, worst of both worlds between chapter 4 and chapter 6, right? And this is not something that we can deal with by methods that we saw before today, but we can still make the smart alecky comment. I can observe that everything here is at most a first derivative, right? Oh, I mean, yeah, that y2 double prime is a first derivative. It's just a first derivative of y2 prime. Right? So identify what are the items that you need to refer to in order to make that smart alecky comment that everything up there is a first derivative. Identify what those things are. It's y1, y1 prime, y2, y2 prime. Give them names. We're going to call them u1 through u4. Whatever. You can call them u0 through u3 if you prefer. It doesn't matter. And then write down the derivatives of those things. You get this. Let's walk through and see how did we do that. What is u1 prime? We'll look at those two equations. u1 prime is clearly u2. Right? Likewise, these two equations tell me that u3 prime is u4. What about these other derivatives? What is u2 prime U2 prime, okay, well, let's see here. U2 prime, here's U2. I need to take a derivative of both sides there. Notice that U2 prime is Y1 double prime, and Y1 double prime is right there. Namely that, I missed. And that goes there. Everybody on board? And then likewise, U4 prime, well, taking a derivative of both sides of this equation, U4 prime is Y2 double prime, which is that, which is this, which goes there. And notice what I've got now. I have successfully turned a second order system that I don't know how to deal with, right? No previous methods of how to deal with it. I have successfully turned that into a first order system that we totally know how to solve. I mean, it's a little inconvenient, right? I mean, we got to find the eigenvalues and the eigenvectors. Come on, diagonalizable. I hope that works out. If not, okay, we might have to find a Jordan basis, and there's going to be a whole thing, right? But the point is, this is something we can do. We've turned a problem that was intractable into a problem that's merely inconvenient. And that's tremendous progress. Yeah? Everybody see how that works? So it's the same idea, right? So this is, again, don't abandon an idea like this one, here, between these two options. Which would you rather? Well, for crying out loud, of course I'd prefer to have that one. So, but if you just abandon the idea, natural though it is, you never know when a future circumstance might come up where that idea that was useless in that context is essential in a different context. Okay? Any questions? Okay. We got a couple minutes, so I'm going to show you an example. The example I'm going to show you, and I'll be real quick about it. This comes from section 6.6. 6.6 is not on the syllabus. It's not required. But all section 6.6 is an example of how to take advantage of section 6.5. So think of 6.6 as being, it's not a liability that you're not responsible for. It is a resource that you can take advantage of. Think of it in those terms, right? And so here's the question that it deals with. It says, suppose you have a mass on a spring. There's our old friend mass on a spring, but now suppose that I attach another mass on another spring. Right? And now I'm going to take this, again, here's the support, spring, mass, and it's sitting there. And now I'm going to pull the whole thing down in some weird way and let go. And I'm going to watch, with one mass, it just, you sort of know it's going to do kind of like this, or maybe the amplitude will decay, or maybe it'll sort of, exponentially kind of asymptotically approach the natural point, whatever. But what's going to happen with two masses, with two springs? Well, you're going to, can you even model this? It's going to do something wacky and chaotic, or so you would think, right? But it's not chaotic at all. You can write down all of the forces that apply to this mass. There's only a handful of forces applying to that mass. That spring is pulling it that way. This spring is pulling it that way. You got F equals ma, you got friction, possibly some external forces, whatever, right? But you can totally write down for that first spring, here's the first spring pulling it up, here's the other spring pulling it down, right? Here's your possible friction, possible external forces, and then you can do likewise for the second one, and check it out, you've got yourself a second order system. So this is not at all a chaotic situation. This is write down the differential equations and solve. And go through the details. You got to kind of collect terms together, just, be organized. Play the usual trick. Play the game that we did previously. And here is the first order system first order 4x4 system that you can solve and describe exactly what the behavior is of those two masses on a spring. Completely tractable. Any questions about this? I mean, there's a lot of details that I skipped over. It's not really the point. Everybody good? Okay, that's all we need to do. All right, see y'all later. Good luck on the final. See you in a week for the final exam. Y'all enjoy LDoc.